I'm going to label a few parts on this diagram here of our double slit interference pattern that we find. And I want you to tell me what those parts are. Okay, first one is the width of the opening. Tell me, is that lambda, d, theta, n, or x, or l? It's going to be d. Little d is the distance between the slits. That can be measured in whatever units we want, meters, centimeters, kilometers if we want, but it makes sense usually to put it into meters. Bottom line is we got to be consistent with all our other variables, and meters ends up being the easiest thing to do with our other variables. All right, what about this one here? The distance from the screen to the openings. That's going to be, which one is it, L or X? Let's go with L. Okay, L is the distance between the slits and the screen. L is going to be a bigger number than X, almost always at least. L is going to be a bigger number than X. In fact, we hope it's way bigger than X, at least 10 times bigger than X. And we'll talk about why that is in just a second. What about this variable right here? It's not L, obviously. It's not D, obviously. Theta, N, lambda, X. This one's going to be X. What about this one? This one's going to be? That one's going to be X as well. And of course, this one is going to be X as well when we're going from a minimum to a maximum. What about N? N is that one that we said has to be consistent with either X or theta. We haven't measured theta. Theta is always measured from the central maximum to one other maximum, or from the central maximum to one of the minima. N has to be consistent with either theta or X. What does N mean? What's N? Yeah, it's the difference between the number of nodes or antinodes. What's N going to be for this one right here? It's going to be 2, because we're dealing with, say, 0 maximum, the central maximum, first, second, third. 3 minus 1 is 2. So little n is going to be 2 in that case. What about in this case right here when we're going from the second order minimum to the third order maximum? What's n going to be? N's going to be 1.5. It's like we're going from the 1.5 maximum, although of course it's not a maximum, it's a minimum, it's a dark spot. But it's like we're going from the 1.5 maximum to the 3 maximum. 3 minus 1.5 is 1.5. What about this one? Going from the second order max on one side to the third order max on the other side. What's it going to be? It's going to be 5. Yeah, 3 minus 2, or 2 minus 3. It doesn't really matter which way you go. You get the same answer there. All right. Lambda, of course, represents the wavelength. These two equations are almost always both valid. The first one is always valid, and the second one is the one that's usually valid. Tell me when tell me the situation in which that bottom equation is not valid. When can I not use it? Good. When L is less than 10 times X. L is virtually always going to be bigger than X. In fact, it probably will always be bigger than X. In fact, most times, L is going to be more than 10 times greater than X. But if it's not, if L is not 10 times greater than X or more than that, then you can't use that bottom equation. It's always an approximation. It's never perfect. But it's, at small angles, close enough that it's going to give us the correct answer to a reasonable number of decimal places. But if we've got a big enough angle, i.e. if L is bigger than 10 times the value of X, then it's just not very good of an approximation, so we're not going to use it. Then we go back and use this one. All right, we had a couple of questions for homework last night, 1, 2, and 3 on 693. In addition, we had worksheet number 19, a couple of questions on that one as well. Any issues that we want to see, that we want to go over here with page 693? Dan? 1 and 3? Okay, 1, 2, and 3 all involve this whole lines per centimeter or lines per meter thing. What's the deal with that? What's the deal with, say, 2,500 lines per centimeter? That's not one of the variables that we identified on this diagram here. Yep. Good. It's equal to 1 over d. If you ever see the distance between the openings, it's d. If you ever see lines per centimeter or lines per meter, it's 1 over d. And then from that, we've got to get d. But that's easy. Okay, as long as we have this value, we can flip it over, take the inverse of it, and that should give us the value of d, in centimeters in this case. All right. We've got a strange set of units there. It's lines per centimeter, not meters. Centimeters, centimeters. Okay, let's circle some more givens here. This is going to be 1 over d. We've got this value right here. That's going to be x. That's the distance between antinode and node. And then we've got L as 50 centimeters. We want to find the wavelength there. It's probably not a bad idea even to circle the fact that this is a node as opposed to an antinode, dark spot. And when we're dealing with dark spots, we're dealing with a 0.5, something 0.5 for the value of n. What is the value of n there? If we're going from the central antinode to the third dark node, or from the central antinode to the third dark spot, what's the value of n? 2.5. Draw it out if you have trouble visualizing that. Okay, this is the central max, first order max, second order max, third order max. We're going from the central antinode to the third dark node, which would be right here, third dark spot. Of course, we're going from 0 to 2.5, so n would be 2.5. All right, let's say lambda is equal to xd over n times L. Is L more than 10 times greater than x? What's the value of x there? 20 centimeters. What's the value of L? 50 centimeters. Is L more than 10 times greater than x? No, so we can't use that equation. For the first time, we've encountered a question where we can't use that equation. So here's what we're going to do. Let's find theta. We know the distance here for x between 0 and 2.5 is going to be 20 centimeters. We know the distance from the screen to the openings is 50 centimeters. Let's find the angle. We can find the angle by saying tan theta is equal to opposite over adjacent. So tan theta is equal to 20 over 50. Theta is equal to the inverse tan of 0.4. What do we get for that angle there? 21 degrees. 21 exactly. 28.8. That's a big angle. If we're above 10 degrees or so, then we don't want to go with that equation. We want to go with the sine theta equation. So clearly we're at 21.8 degrees. We've got to go with that other equation. Lambda is equal to d sine theta over n. D has a value of, we're not sure actually, we've got to find that. D is 1 over 2,500. What do we get for that? 4 times 10 to the negative 6, and that's going to be centimeters, right? We want to convert that to meters, so it's going to be 4.0 times 10 to the negative. Okay, so that's 10 to the minus 4. So that's going to be 4.0 times 10 to the minus 6 meters then. That's what we want here because everything else is going to be meters as well. 4 times 10 to the minus 6 times sine 21.8 over little n, and a little n was 2.5. We get the value for lambda there is what? 5.9 times 10 to the minus 7 meters. And we got a number that's 10 to the minus 7, so we're probably right, no guarantees. Let's just real quickly do it the other way, using xd over n times L, and see what we end up getting. See how far off it ends up being here. Is that right? Is there a mistake there? Yeah, because in the book, they assumed this equation to be valid, and it's not. It's not. What did they end up getting? Times 10 to the negative 7. So you can see you're in the same ballpark there, but you can see that if you use that equation with such a big angle, 21.8 degrees, then it doesn't give you, clearly it doesn't give you the right answer. Okay? Assuming that is the correct answer, that is. All right, so if you got an angle that's bigger than 10 degrees, and the rule of thumb on that is if x is bigger than 1/10 of L, then we're not going to use that equation. Yep. No. If you've got an angle less than 10 degrees,
But they assume that even if, this book uses the one angle, but they'll never do that, right? They won't make the answer off of this equation.
No. Yeah, the textbook, what happens with a textbook when they write a textbook is you probably should have more proofreaders than you actually have. I mean, there was a million mistakes in this textbook when it came out. It's a good textbook, but there's a million mistakes in it. What happens is somebody writes a chapter or whatever, and then somebody proofreads it. Maybe a couple people proofread it, and then it gets published. There's mistakes all over the place. On the diploma exams, somebody writes a question, and then that question gets read by, it probably goes through 50 people, at least before it actually appears on a real diploma exam. So the odds of a mistake like that happening would be minuscule. It almost certainly wouldn't happen. It gets field tested, for heaven's sake. So what happens when all these results come back, all these people got this number, and they had it keyed to this? It's like, oh, wait a second, maybe we should check that to make sure that we haven't made a mistake. So all those checks and balances to make sure that that doesn't happen. Okay? You can be pretty confident that it wouldn't. Now, if you're dealing with a small angle, if L is going to be bigger than 10 times x, then you should be able to use either equation. Even if there's just a rounding thing that causes one to be 5.93 and the other one is 5.92, using the other equation, they'd accept both because they would have thought of the fact that you could have used both equations there. Yep. Yes, they will. Yeah. Most times they're going to be the same answer if you're dealing with a small angle. But in that event that one is 5.925 and one is 5.924 and gets rounded down, then they'd accept both of them. Yeah. All right, question number 3 says a diffraction grating has 1,000 lines per centimeter. That's going to be 1 over d again. And of course, we're in centimeters here. We don't want to be in centimeters. We've got red light, wavelength 750 nanometers is incident on the grating. What's the separation between bright antinodes on a screen 3 meters away? This is going to be L. We want to find X, the separation between antinodes. Now, they don't actually say this, but what they mean when they say the separation between antinodes is the separation between adjacent antinodes, or antinodes that are right beside each other. So therefore, n will be equal to 1. All right, let's try that equation. Lambda is equal to xd over n times L. Is L greater than 10 times x? We don't know here, do we? We don't know. Okay, if you ever come across a question like this where you don't have the value of x and L and you don't have a theta, you just have to assume that this equation is valid. Okay, whether it is or isn't, you have to assume, because you can't find theta without x, and you can't determine whether this equation is even valid without x. So you got to assume that it is. Okay, it's not a great situation, but it happens, and we just have to make that assumption. Let's solve for x here. Lambda times n times L over d. Let's say lambda is 750 times 10 to the minus 9. N is 1. It's easy when n is 1. Easier when n is 1. L is 3 meters away. And we divide that by d. D, it's 1 over d is 1,000. So we're going to say d is 1 over 1,000, which is 0.001 centimeters, or 0.001 times 10 to the minus 2 meters. If we want to just move the decimal place over a couple places, that's okay too. I'm not a fan of doing that. I like to just tack on the exponent when I'm dealing with a decimal number like that. To me, it's just easier, but whatever works for you. All right, 750 times 10 to the minus 9 times 3 divided by 0.001 times 10 to the minus 2. Let's see if we can get the answer here. It's going to be 2250 times 10 to the minus 9 divided by 1 times 10 to the minus 3, so it's going to be 2.25 times 10 to the minus 6. Is that right? No? What's the exponent? (2.25) times 10 to the minus 1 meters. There we go. 0.225, 2.25 times 10 to the minus 1. We're good with that? All right, we also had 3 questions on that worksheet, number 19. Questions 1, 3, and 4. We'll give you the answers for those questions right now. For question number 1, we got 3.64 times 10 to the minus 7. number 3, I should say, we got 4.47 times 10 to the minus 6. Question number 2 was missing some data, so we skipped that one. Question number 4 was 2.88 times 10 to the minus 6 meters. Any issues on 1, 3, or 4 on worksheet number 19 that we'd like to go over here? Rob? 4? Okay, 3 and 4? Okay, 3 says, how far apart are the slits on a diffraction grating if the third order maximum is seen to be 25 degrees from the central maximum when using light of wavelengths 630 nanometers? The angle here is obviously 25.0 degrees in question number 3. The wavelength is 630 times 10 to the minus 9 meters. We're looking for D, the distance between the slits. And what else do we got here? N? What's N? We're talking about the third order maximum as measured from the central max. N will be equal to 3. So we're going to use the equation lambda is equal to d sine theta over n. We don't have to do a check here to see if it's valid because this one's always valid. Is L greater than 10 times x? We don't know because we don't know what either one of them is. But in the end, it doesn't even matter because this equation is valid whether it is or isn't more than 10 times greater. Let's rearrange this equation, solve for d. It becomes lambda times n over sine theta. So 630 times 10 to the minus 9 times 3 divided by sine 25 degrees. We do that, it should work out to be 4.47 times 10 to the minus 6. Good? And number 4 says light of wavelength 530 nanometers is shown on 2 slits. We're going to say lambda in this one is 530 nanometers, or 530 times 10 to the minus 9 meters. We want to find the distance between the slits, little d, if the angle from the central max to the second minimum is 16 degrees. What's n going to be if we're talking from the central max to the second min? Central max, first max, second max, third max. We're looking for this, right? N between there, between the central max and the second order minimum. What's n going to be? 1.5. So once again, let's say lambda is equal to d sine theta over n, or d is equal to lambda times n over sine theta. 530 times 10 to the minus 9 times 1.5 divided by sine 16 degrees should give us 2.88 times 10 to the minus 6 meters. Is that one okay? Yep. And you didn't get the answer? Okay, we'll go through that then. Okay, let's sub in our values here, and then we'll pull up the calculator and go through it. 530 times 10 to the minus 9 times 1.5. And then we say sine 16 degrees on the bottom. All right, let's say now on the calculator 530 times 10 to the minus 9 times 1.5. Just follow along on those keystrokes there, Nick. Let's press equals, and let's divide that by, I'm not sure if we have to use brackets on the bottom there or not. I don't think we do, to be honest, but if in doubt, use brackets, right? Divide that by sine 16 degrees. Make sure you're in degree mode. Okay, let's end the brackets around the 16. Let's end the brackets around the sine, and we end up getting 2.88 times 10 to the minus 6. Okay. Yeah. You're getting it now, though? Okay, good. All right, what I'd like you to do right now, please, is to flip over the page and take a look in class here, just for the next few minutes, at question number 6. Question number 6 is missing a little bit of data, but I'll tell you what that is right now. The distance from the screen to the slits is 2.00 meters. In fact, it's going to be 2.00 meters for questions 6, 7, and 8, although I'm only asking you to do question 6 right now. So the distance between the slits and the openings, L, is 2.00 meters for 6, 7, and 8. All right, take a couple minutes, see what you can do with number 6, and then we'll take a look at it. Let's take a look at question number 6 on our worksheet now. It says light with a frequency of 6.00 times 10 to the 14 hertz. Okay, let's write that down right away. 6.00 times 10 to the 14 hertz is shown on a diffraction grating that's scored with 5,000 lines per meter. That means that we don't have the value of D, but it's close. We have 1 over D. It's 5,000. And it's in lines per meter, so we don't have to worry about any kind of funny units there. We want to find the distance between the second order max and the fourth order min. We want to find X. We know that L is equal to 2.00 meters. What's N here? From the second order max to the fourth order min. Here's the central maximum. Here's the first max, second max, third max, fourth max. We're going from the second order maximum from here to the fourth order minimum. 1, 2, 3, 4. Fourth order minimum. What's N going to be there? What is it, Dan? Good, 1.5. It's 3.5 minus 2. N is going to be equal to 1.5. So let's write down our equation now. Let's say lambda is equal to x d over n times L. Again, we have to assume this. We can't find theta because we don't know what x is. And we can't tell if L is more than 10 times greater than x. So we just have to assume this equation is correct and hope for the best here. Let's rearrange this to solve for x. Becomes lambda times n times L over d. Lambda is, we told the wavelength here? We're not, are we? We got to find the wavelength here from the frequency. How are we going to do that? Yeah, it's V over F. Okay, it comes from that wave equation in physics 20, V equals F times lambda. So it's 3 times 10 to the 8 divided by the frequency of 6 times 10 to the 14. That gives me a wavelength of 5.0 times 10 to the minus 7 meters. Let's sub that in. 5.0 times 10 to the negative 7 times n, which is 1.5, times L, which is 2.0. Let's divide that by d. We don't know what d is either, but we can find it. d is equal to 1 over 5,000, which is 2.0 times 10 to the negative 3? 4? 2.0 times 10 to the minus 4 meters. When we do the work on that one, it should work out to be 7.5 times 10 to the negative 3. What's the problem, Rob? Did you get the wrong answer? You got point what? Okay, that's 7.5 times 10 to the minus 3. Good. Just work on that converting from standard to scientific notation, and you'll be good there. Is that question okay? All right. The last one that I want to do here with you, and I do want to go over this one with you, is question number 9. It's a real challenge question. I'd like you to take 30 seconds just to see if you can grab some thoughts. But don't worry about actually trying to solve it. We'll solve it as a group here, okay? All right, let's take a look at question number 9 now. This is a real challenge question. And to be honest, I wouldn't anticipate that you'd get a question as difficult as this on a test or an exam, but you never know. I think it's a good exercise to go through to stretch your mind a little bit, but it's also a good exercise to go through on that off chance that you do see something that's just difficult on the test or on the exam. It says white light is directed on a diffraction grating ruled with 5.0 times 10 to the 4 lines per meter. White light. White light consists of all the colors of the rainbow, but they're all combined. When it hits the diffraction grating, what's going to happen? Well, same thing as what happens when it hits a prism. It's going to split up for a different reason. It splits up when it hits a prism because refraction happens a different amount for each different color. When it hits a diffraction grating, diffraction happens a different amount for different colors. Lambda is equal to xd over n times L. Lambda is equal to d sine theta over n. If theta is different, if lambda is different, then theta is different, and you're going to see the maximum in a slightly different spot. So the effect of it is that it's going to split up the colors just like the prism, or at least almost like the prism. If you look at it closely, the prism splits the colors up into red, orange, yellow, green, blue, indigo, and violet. If you look at the diffraction grating, it actually splits it up into violet, indigo, blue, green, yellow, orange, red. So it splits it up into the opposite direction. We talked about that earlier on when we were first introduced this whole of diffraction and interference. So what pattern do you see? Well, the central maximum would be white light. The central maximum doesn't split up because it's going essentially straight through there. Okay, it's going to be white light. Now, I can't really draw white on a white screen, but let's say the maximum is inside this box here. It's white light. Then beside that, you're going to get a first order maximum that consists of red on the far side, orange, yellow, green. What's the indigo here? Blue. I guess we're missing blue. Indigo, you get the idea, right? Roy G. Biv, except backwards there. I know my blue and my indigo and violet are pretty much the same colors, but it's okay. You get the idea. So we're going to see that first maximum, but that first maximum is going to be all the colors. We're also going to get a second maximum, which is once again going to be all the colors, and a third maximum, which is once again going to be all the colors. We're going to get the same thing on the other side as well. Red is on the far side this time again. Red is furthest away from the central maximum, and then of course blue and violet is going to be closest to the central max. So does that make sense so far? We've got all our maxima here, the same as we always have, but because we have different colors, we actually end up with more than one first maximum and more than one second order maximum and so on. We end up, if we just had red light going through there, then this would be where we see our first order maximum. If we just had violet light going through there, then this is where we'd see our first order maximum. But because we have red and violet and every color in between, what we get is a maximum that's this wide, the width of the distance between red and violet. All right, we've got a diffraction grating that's ruled with 5.0 times 10 to the 4 lines per meter. That allows us to find D. It's going to be 1 over 5 times 10 to the 4. That's going to give me 2.00 times 10 to the minus 5, I think, isn't it? Times 10 to the minus 5 meters. And we can all do that. Okay, we don't have to be able to do what I just did on the top there to recognize that D is 2.0 times 10 to the 5. We're looking for the width of the first order spectrum. In other words, we're looking for this distance right here, okay, whatever variable we want to call that, on a screen that's 1.2 meters away from the grating. So that's going to be 1.2 meters. What's next? Any suggestions here? Any ideas? Okay, let's get the wavelength of the red and the wavelength of the violet. Okay, we can do that by saying the frequency of the red is 4 times 10 to the 14 hertz. We'll call that FR, frequency of the red. The frequency of the violet is 7.5 times 10 to the 14 hertz. And we remember those from the table that we learned on the first day of the unit. Let's get lambda 3 times 10 to the 8 meters per second divided by 4 times 10 to the 14. This is for red light. It ends up giving us 7.5 times 10 to the minus 7 meters. For violet light, we're going to say 3 times 10 to the 8 divided by 7.5 times 10 to the 14. And when we do that math, we end up getting 4.0 times 10 to the negative 7 meters. So now we have our two wavelengths. Now what? XD over N times L? Well, what's that going to do for me? Yeah. We're going to find out X for each of them. We're going to say we're starting at the central maximum here. And then we want to find X to the first order maximum. Let's find X to the first order maximum for red. Let's find X to the first order maximum for violet. And then subtract them. So let's do violet first since it appears first. It's equal to lambda times n times L over D. Lambda is, for violet, 4 times 10 to the minus 7 times n is, if we're talking about the first order max and the central max, n is going to be equal to 1. L is going to be equal to 1.2. And D is 2.0 times 10 to the minus 5. What do we get for xv there? 4 times 10 to the minus 2? 4.0 times 10 to the minus 2? No, that is wrong. It's not 4. What'd you get, Patrick? 0.024 meters. All right, so this distance right here is 0.024 meters. That's x, the distance from the middle of the central maximum to the violet bright spot. But then that red bright spot is still part of the first order maximum, but it's going to be a different distance. So let's find its value. Let's find x now for red. It's going to be equal to lambda times n times L over D again. But lambda this time is 7.5 times 10 to the minus 7. N is still 1. L is 1.2 meters. And D, that distance between the slits, is 2.00 times 10 to the minus 5. What do we get for x this time? 0.045 meters. All right, so this distance here now, 0.045 meters to the red side of that maximum. If it's 0.024 to the blue side of the maximum, 0.045 to the red side of the same maximum, then the maximum must be the difference between those two x's, 0.021 meters. Patrick, did you get that answer? 0.021? Good. Anybody else on the right track? Maybe just didn't have enough time, or at least have that thought. That's a tough question, but does the logic of it make sense now? Good. It's a great question to illustrate, some pretty tricky logic, but it's also a great question to illustrate what actually happens when you have white light going through, not just one color. In the end, that part of it doesn't need to be hard, right? If we have red light going through, then the red maximum is going to be formed right there. Okay, we can do the math on that. If the blue light's going through, then the blue maximum is going to be formed right here. Okay, we can do the math on that one. The first order maximum happens to be that, both of those maxima, and then all colors in between. Dan? Yeah, Dan's question was, what would the spectrum look like going through a prism? We would see, let me create a new page here, Dan. Okay, we would have, on a diffraction grating, we would have our white light, and then we would have our next maximum that is going to consist of, my violet light all the way through to my, my other colors all the way through to my red light, right? And we're going to have a bunch of those. That's the first order max. And then we got our, it's not working out so well, but you get the picture here, right? We get our central, we get our first order max, we get our second order max, we get our third order max over there. We get the same thing on this side, our first order max, our second order max, our third order max, and so on. Each maximum is a rainbow, but it's in reverse direction. It's not red, orange, yellow, green, blue, indigo, and violet. It's violet, indigo, and so on and so on and so on. And that's when white light goes through a diffraction grating. When white light goes through a prism, what we end up getting is one spectrum. Instead of multiple spectra like this, we get one spectrum, and that one spectrum is in the reverse order. Instead of being blue, violet, indigo, blue, it's red, orange, yellow, green, blue, indigo, and violet. So red gets refracted the least, red gets diffracted the most. Violet gets refracted the most, violet gets diffracted, at least. So similarities, hey, we can break up the light into its component colors. Differences, well, the component colors are going to be in the opposite direction. And with the prism, we only have a single spectrum produced. With the diffraction grating, we have multiple spectra produced. Go ahead. Question?
When you found the frequency for red light and violet light,
Yeah.
you used that table we did in the very beginning.
Yeah, I just had those memorized, yeah. Yeah. Blue light is, well, we don't have to have the specific colors memorized, but we do know the range of frequencies for visible light was 4 times 10 to the 14 to 7.5 times 10 to the 14. So the extremes, call them what you want, the extremes are 4 to 7.5 times 10 to the 14. So we can find the corresponding wavelengths to those. All right? All right, that's a good question, guys. We're going to shift gears a little bit here now and talk about something called photon theory. Early on in this unit, in fact, on the very first day, we talked about light. We talked about EMR, electromagnetic radiation, as being a wave. And we identified 4 properties that it exhibits that illustrate the wave nature of that light or of that EMR. One of them was refraction. Waves refract. Refraction is a property of waves, and since EMR refracts, then EMR must be a wave. Another one was diffraction. Diffraction is a property of waves. Since EMR diffracts, then EMR must be a wave. Interference is another one. Interference is a property of waves. Since EMR interferes, it must be a wave. And then finally, the last one is polarization. That's the one where we had the 2 polarizing filters and we rotated them and we found that it blocked out all the light. Polarization is a property of waves. And since EMR undergoes polarization, then it must be a wave. But there's other observations that have been made throughout history that have indicated that EMR is not a wave, that EMR is a particle. In fact, there was a discovery made in 1887 by Heinrich Hertz. He's the guy that did that spark gap apparatus verifying Maxwell's theory of electromagnetism. He discovered something called the photoelectric effect. We'll talk in a lot more detail about that over the next couple of days. But essentially, for the next 20 years, nobody could explain it because we had accepted the wave particle or the wave theory of light, and the wave theory of light wouldn't explain the observations that were made with the photoelectric effect. So nobody could explain what was happening. We saw what was happening. We have this wave theory of light, but the wave theory of light and the observations that are made in this photoelectric effect just didn't agree with each other. So we fast forward almost 20 years to Einstein. Okay, Einstein's name, probably the most famous physicist ever, actually. You're going to hear his name lots now between now and the end of the year, but today you're hearing it for the very first time. Einstein in 1905 had what we call his miracle year. Most people in their entire lives don't have a single original thought. And that sounds bad, but it's true. Most people think about things that have already been thought about by somebody else. Einstein came up with 4 brand new original thoughts in 1 year in 1905. He worked in a Swiss patent office. During the day, he went to work just like everybody else, and he reviewed patents to see if this invention was worthy of getting a patent or not. At night, he went home and he thought about things. And he, as I say, he came up with 4 original thoughts that were published that year in 1905. Hence, the miracle year. Most people don't do it in their entire lives. He did it in 1 year. 4 of them in 1 year. One of those miracle thoughts was this idea that we call photon theory. The idea that light isn't a wave, or at least that it's not just a wave, but that light has a particle nature as well. Photon theory, particle theory of light. Light, or EMR in general, is a bundle of energy, a quantum of energy, or a particle of light. So as opposed to seeing this wave, we picture the light as these little pebbles, these little rocks, or these little baseballs that are coming towards us. Okay? These little particles called photons that are coming towards us. Now, currently, the model that we accept today is kind of a mix of the two, the wave theory of light and the particle theory of light. We say that light has a wave nature. Okay, we haven't abandoned that. but we also say that it has a particle nature. We'll talk about the evidence that supports the particle nature over the coming days. Okay, for now, okay, you have to just trust me that Einstein in 1905 came up with this idea of the photon theory, and it explained the photoelectric effect, which for the previous 18 years, nobody could explain. Hence, the general scientific community said, we'll pretty much have to accept this photon theory then. It pretty much has to be right. If it explains something that's never been able to be explained before, then it must be correct. Photon theory, the particle theory of light. A photon is a bundle of energy, a quantum of energy, or a particle of light, like a rock is a bundle of energy. You throw a rock, it has a certain amount of kinetic energy. Well, a photon has a certain amount of energy as well. Okay? It's a particle that contains a certain amount of energy. Now, we can describe the energy of a rock with the equation EK is equal to 1/2 mv squared. We can't describe the energy of a photon with that equation because a photon doesn't have any mass. A photon is massless. Einstein described the equation of a photon, or the energy of a photon, I should say, with this equation, E is equal to hf. Don't worry about what h is right now. But f is the frequency of the EMR. So effectively what Einstein was saying is that, this is a bit counterintuitive, the energy of the EMR is not related to necessarily the amount that you have, but the energy of the EMR is related to the type of EMR that you have, the frequency that you have. In other words, violet light would be more energetic than red light. Ultraviolet would be more energetic than visible light. X-rays and gamma rays would be the most energetic EMR, not because it's moving faster, not because there's more of it, but because it has a higher frequency. Now, because E is equal to h times f, E is also equal to hc over lambda. Of course, f is equal to c over lambda, so those two equations gel with each other. What's h? H is a constant. We call it Planck's constant. It's kind of weird here, but Planck's constant has two values, 6.63 times 10 to the minus 34 joule seconds, but it also has a value of 4.14 times 10 to the minus 15 joule seconds. Electron volt seconds. How can you have two different values for the same number? If it's a constant, isn't it just one number? Different units, yeah. I drove from Okotoks to California and Arizona last summer, and then back up to Okotoks last summer. Utah is probably the funnest place in North America to drive, or at least the funnest place that I've ever been to in North America to drive, because the speed limit on the highway in Utah is 85 miles per hour, which is 136 kilometers per hour. You can set your cruise control at 135 and be going under the speed limit. Now, you burn a lot of gas. I ended up actually going a fair bit slower than that, only because I wasn't getting very far in a tank of gas. The speed limit is 85 miles per hour or 136 kilometers per hour. Okay, it's a constant, right? It doesn't matter whether you call it 85 miles per hour or 136 kilometers per hour. It means the same thing. You can see how we can have two different numbers that describe exactly the same thing as long as they have different units associated with them. Nick made that point with this, right? These are two different numbers, but they describe exactly the same thing because they have different units associated with each other. Joule seconds and electron volt seconds. Now, which one do we use? Usually it's whatever one's convenient. There's going to be a few times when we can't use one or the other, and we'll talk about that as we encounter them. But for now, we're going to use whichever one's convenient. We're going to do 3 example problems here today. Okay, the first one, really straightforward. How much energy is carried by a photon of red light that has a wavelength of 600 nanometers? Let's use E is equal to hc over lambda. H times F is also valid, but since we don't know what frequency is, we do know what wavelength is. We might as well use this. Now, what value of Planck's constant do you want to use here? 6.63 or 4.14? Yeah, 6.63, sure. You could use 4.14 though as well. Doesn't matter. If we use 6.63, what's my energy going to be measured in? If I use the 6.63 value, then my final energy is going to be measured in joules. If I use the 4.14 value, my final energy is going to be measured in electron volts. So it doesn't matter. Just understand that whichever constant you use determines what units your final answer is in. So Patrick said 6.63 times 10 to the minus 34 joules seconds. Multiply that by 3 times 10 to the 8 meters per second. And we divide that by our wavelength, which is 600 times 10 to the minus 9 meters. That's going to be 3.315 times 10 to the negative 19 joules. And we should round that really to 3.32 times 10 to the minus 19 joules. Again, had you did that with the other value of Planck's constant, you would have got a number that was completely different than that. That's okay, as long as you expressed it in electron volts, not joules. Let's take a minute or two and look at these questions on 706, please. Let's take a look at the next one here. This one's a bit tougher. Same basic concept, but forces us to think just a little bit harder here. It says your eye can detect as few as 500 photons of light. Your eye is most sensitive to light having a wavelength of 510 nanometers. What's the minimum amount of light that your eye can detect? The minimum amount of energy that your eye can detect. Well, let's find the energy of a particular photon of light. This light that has a wavelength of 510 nanometers. E is equal to hc over lambda. Let's use 6.63 times 10 to the minus 34 joules seconds. It's going to put our final answer in joules as well. Multiply that by 3 times 10 to the 8. And let's divide that by 510 times 10 to the minus 9 meters. Gives us an answer for the energy of a particular photon, one photon, and it's measured in joules. We get 3.9 times 10 to the minus 19 joules. The energy of one photon, a single photon, 3.9 times 10 to the minus 19 joules. Now, if our eye needs 500 photons in order to see it, 495 photons strikes our eyes, we can't detect it. Then what do we got to do with this energy of one single photon to get the total amount of energy here? How much energy does our eye need to detect if we need 500 of these photons? What are we going to do? Times it by 500. Multiply that by 500, we end up getting 1.95 times 10 to the minus 16. So the total amount of energy that our eyes need to strike it in order to detect the EMR is going to be 1.95 times 10 to the minus 16 joules. So mathematically, it's no harder than the other question we did as an example. But conceptually, it's a little bit tougher because you've got to do that multiplication. We have some practice problems on 707 as well, and we have one more example that we want to finish up here today. It says, how many photons are emitted each second by a laser pointer that has a power output of 0.400 milliwatts if the average wavelength produced is 600 nanometers? This one's the toughest of the three, I think. We're looking for the number of photons. The last time we were asked for a number of something, it was the number of electrons. And we took the total amount of charge and divided it by the charge of one electron. Here we're looking for a number of photons. So it's going to be the total something divided by the something for one. But since it's photons, it's not going to be charge. We have a power here of 0.4 milliwatts. We have a wavelength here of 600 nanometers. We have a time here of 1 second. Doesn't say that, does it? What's the number of photons each second? What's the number of photons in 1 second? What's the time? 1 second. We know that power is equal to energy over time. That's a physics 20 thing. Energy is therefore equal to power times time. The power is 0.400 times 10 to the minus 3 watts. The time is 1 second. That gives us a total energy of 0.400 times 10 to the minus 3 joules. That's the total energy. Now, the energy for one photon is simply going to be equal to hc over lambda. That's 6.63 times 10 to the minus 34 times 3 times 10 to the 8 divided by 600 times 10 to the minus 9. That's going to give us 3.315 times 10 to the minus 19 joules, I believe. Is that right? Now that we have the energy for one photon, now that we have the total amount of energy, how are we going to find the number of photons? You guys know this. Okay, we haven't done this with photons before, but we've done it with electrons. How are you going to get the number of anything when you have a total and you have the something for one? Yeah, divide the two. Let's go 0.400 times 10 to the minus 3 joules divided by 3.315 times 10 to the minus 19 joules. We do the math on that one, and it should give us our answer for the number of photons. 0.4 times 10 to the minus 3 divided by 3.315 times 10 to the minus 19 gives me 1.21 times 10 to the 15 photons is our answer. All right, your homework, obviously for tomorrow we have our test. If you have a chance, get these questions done as well, but I won't be here tomorrow. Okay, so obviously we won't be checking them over till Thursday. The homework will be these questions on 708. In addition, I want you to do the questions on 707 that we kind of skipped past there. And then 706 that I gave you time for in class. If you haven't finished those already, let's get those done as well. 706, 707, and 708.
Mrs. F's office, please.